The total magnetic flux out of the Earth exactly equals the flux into the Earth. But just where does the planet's flux come from?
The Earth's main magnetic field we know to be caused by the flow of large-scale electric currents deep inside the Earth. There are other components to the field, but the main field, the dipolar component, is associated with these currents. We don't know exactly how the magnetic field is produced. We don't have an accepted model in detail for the production mechanism. However, we know it's somehow related to the motion of these molten conducting materials and the rotation of the Earth, and those materials are, especially in the deep interior, primarily molten nickel and iron.
Because the Earth's magnetic field stems from the rotation of the Earth, it more or less lines up with that rotation. In reality, the whole field wobbles around once each day because it's off by about 11.5 degrees. That difference has been known since antiquity, and explorers have always had to compensate for it, some more successfully than others. But even for the best sailors, the Earth's magnetic field doesn't quite stay put.
The Earth's magnetic field is continuously changing. As a matter of fact, the navigational charts, the things that we use to determine our direction by using the measurements with compasses, have to be changed every so often in order to be sufficiently accurate for navigational purposes. So the field is constantly changing. Over the scales of millions of years, it changes much more dramatically than that, and in fact, the polarity actually reverses, not in a periodic way, but in an aperiodic way, nevertheless, frequently in terms of geologic time.
From a geologic point of view, this flipping of the Earth's magnetic poles, north for south, takes place fairly often, about every 500,000 years or so. Compare that cycle to how often the sun changes polarity.
The field of the sun changes direction every 11 years, and this is a remarkable process which starts with the sunspots. The magnetic polarity of sunspots is different in each successive 11-year cycle. A sunspot is a dark region that we see on the surface of the sun, which we find is the result of intense magnetic fields. The sunspots always occur in pairs because there are no magnetic monopoles, so I always have to have a north and a south, or a plus or a minus polarity together. So I tend to see two big sunspots, and the magnetic lines of force will go from one sunspot into another. We see the sunspots come up as though a big tube of magnetic flux has come up from below the surface, and we see the intersection of this tube with the surface as a very strong sunspot.
Very strong sunspots create very strong consequences. Among the most spectacular are the solar flares. There's also the solar wind, not as obvious but equally evident when it whips out to play havoc with the Earth's magnetic field.
The sun is the origin of the solar wind, which is a high-speed outflow of all the material in the atmosphere of the sun. And this happens in a curious way. The outer atmosphere of the sun, which we call the solar corona, is very hot. That's what we see around the sun at a total solar eclipse, if you ever get to see one. It's 1,000,000 degrees in temperature. Now, when the gas gets that hot, it becomes easier for it to escape from the sun. Because it's so hot, the conductivity is high, and so the temperature of the solar wind stays high a long way out. Even at the Earth,